Hello, good morning, students. In the last lecture, we had studied disaccharides. We know disaccharides which on hydrolysis give monosaccharides, or a carbohydrate which on hydrolysis give 2 units of monosaccharides are called disaccharides. In our syllabus, 3 examples of disaccharides are given. One is sucrose, second is maltose, and one more is lactose. In the last lecture, we had studied this structure of sucrose. We know sucrose is a disaccharide having molecular formula C12H22O11. It is dextrorotatory, that is, it shows optical activity rotation towards right side by angle of rotation plus 66.5 degree, which on hydrolysis with dilute acid or enzyme used for hydrolysis, it is called as a invertase. Sucrose gives equimolar mixture of D plus glucose and D minus fructose. And the reaction for hydrolysis of sucrose is, it is C12H22O11, it is a sucrose, plus H2O in the presence of dilute acid, that is H plus, or in the presence of enzyme invertase, we get C6H12O6 plus C6H12O6. Out of this, one molecule is a glucose and other molecule is a fructose. Both are dextrorotatory. Here, the Leo rotation of fructose is minus 92.4 degree, is larger than the dextrorotation of glucose. We know the dextrorotation of glucose is plus 52.7 and the Leo rotation of fructose is minus 92.4 degree. So this Leo rotation is more than the dextro rotation. So the hydrolysis product has net Leo rotation because the Leo rotation is higher degree, more degree. Hence, the hydrolysis of sucrose is also called as inversion of sucrose, and hence the product is called as a invert sugar. The structure of sucrose contains glycosidic linkage between C1 carbon of alpha glucose and C2 carbon of beta fructose. This we had studied last time, this ring structure of sucrose, that is one molecule of glucose and one molecule of fructose. They are bonded. Here, this alpha D glucose unit, here the alpha OH group of glucose at carbon number 1 get bonded with beta OH group of the fructose molecule. So this way, this alpha and beta bonding take place, that is called as a alpha beta 1,2 glycosidic linkage. And this structure of sucrose is called as a Haworth formula for sucrose. Then the potential aldehyde, since the potential aldehyde and ketone groups of both monosaccharide units are involved in the formation of glycosidic bond, hence the sucrose is a non-reducing sugar. Remember this well. Sucrose is non-reducing sugar. Last time we had studied glucose and fructose. These are the reducing sugars. The next example of disaccharide is maltose. Second example of disaccharide is maltose. Again, maltose having molecular formula C12H22O11. It is a disaccharide. Again, it is made up of two units of monosaccharides. One is D-glucose, that is both units of monosaccharides are D-glucose. Here the glycosidic bond in maltose, it is formed between C1 carbon of one glucose and C4 carbon of other glucose molecule. Remember this again well, that the glycosidic bond between two glucose molecules is due to C1 carbon of one glucose molecule and C4 carbon of other glucose molecule. The glucose ring, which uses its hydroxyl group at C1 carbon at alpha position, that is alpha glucopyranones. Hence the linkage is called as a alpha 1,4 glycosidic linkage. The linkage is called as a alpha 1,4 glycosidic linkage. Then the hemiacetal group at C1 carbon of second ring is not involved in the glycosidic linkage. Hence, maltose is reducing sugar. Remember the difference between sucrose and maltose. We had studied sucrose is non-reducing sugar, and here the maltose is reducing sugar because the hemiacetal group at C1 carbon of second ring is not involved. This is the second ring. This is the OH group at carbon 1, which is not involved in the glycosidic linkage. Hence, this maltose is called as a reducing sugar. So maltose on hydrolysis give glucose with dilute acid, or here the enzyme used for hydrolysis is maltase. Enzyme used for hydrolysis of maltose is maltase enzyme. So in this figure we will study this Haworth formula for the maltose. Now how this formula can be drawn, I will explain now in detail how this formula of maltose can be drawn. We know here the two molecules of glucose. This is alpha D glucose because at first carbon the OH group is below the ring. Again at fourth carbon in the second ring, OH group is below the ring. So this linkage between first glucose molecule and second glucose molecule is below the both rings. Hence it is called as a alpha glycosidic linkage. It is between first carbon of first ring and fourth carbon OH group of the second ring. Hence it is called as a alpha 1,4 glycosidic linkage. The structure is very simple to remember. We know how to draw structure of glucose. We know glucose contains this O, then first carbon H and OH group, second carbon HOH, third carbon OH above and hydrogen below, fourth carbon HOH, fifth carbon hydrogen below, and sixth carbon is bonded above, that is CH2OH. Exactly similar ring of second glucose molecule here, and the bond formed between these two OH groups, that is first carbon OH and fourth carbon OH, get bonded and gives H2O molecule as a side product. This bond is dash O dash bond between two glucose molecules, and this is the structural formula or Haworth projection formula for maltose molecule. So that is about the structure of maltose. Now we will study this lactose. Third example given in our syllabus, that is of disaccharide, is lactose. Again, lactose having molecular formula C12H22O11. It is a disaccharide. It is present in the milk and it is formed from the two monosaccharide units. These two monosaccharide units are, one is D-galactose and D-glucose. One is D-galactose and other is a D-glucose. The glycosidic linkage is formed between C1 carbon of beta D-galactose and C4 carbon of glucose. Now we will study how this linkage is formed. See, this is the structure of galactose. The difference between the structure of glucose and galactose is that at fourth carbon, OH group is above the ring, that is the galactose, and in fourth carbon in glucose molecule the OH group is below the ring. That is only the difference. All other groups have the same position in glucose and galactose. Now, so this first molecule is galactose and second molecule is a glucose. Here this is beta D glucose, galactose, because first carbon OH group is above the ring, and here this is again glucose molecule which is fourth carbon or first carbon OH group is above the ring, hence it is a beta D glucose. Depending upon the position of OH group at carbon 1 in galactose or in glucose, this alpha or beta structures are there, anomers are there. We had already studied this, but I am explaining this for this detailed study of this galactose. Here the OH group is above the ring at first carbon, OH group is above the ring, so both structures are beta structures. Here this first one is galactose because fourth carbon OH is above the ring, and in glucose fourth carbon OH is below the ring. That is only difference in the galactose and glucose. Now bond is formed, dash O dash bond between two monosaccharides is formed by beta OH group at first carbon and alpha OH group at fourth carbon. This is a glycosidic linkage called as a beta 1,4 glycosidic linkage, and this is Haworth formula for lactose. Now this linkage in lactose is called as a beta 1,4 glycosidic linkage. The hemiacetal group at C1 carbon in the glucose unit is not involved. We had already studied this is a glucose molecule, first carbon OH, that is called as a hemiacetal, and which is not involved in the glycosidic linkage, but it is a free, hence the lactose is a reducing sugar. Remember this again, out of the two disaccharides, maltose and lactose, these are the reducing sugars, but the sucrose is non-reducing sugar because in sucrose this hemiacetal groups are not free, but in maltose and lactose this one of the glucose molecule have hemiacetal group which is the free, and hence the maltose and lactose, these are the reducing sugars. So that is about the structural formulae of sucrose, maltose and lactose. These are the examples of disaccharides. Thank you.